Greetings everyone, this is not an expert here back again with another video. Today we'll be solving problem number 18 and the difficulty it's been rated at is hard. This problem was asked by Google. Again, don't get intimidated by that. And let's just get down to the problem description. So given an array of integers and number k, where k is inclusive of all values from 1 to length of the array, compute the maximum value of each subarray of length k. For example, given an array 10, 5, 2, 7, 8, 7 and k equal to 3, we should get 10, 7, 8, 8. If you didn't understand what the problem is, it's basically it's saying that you need to compute the maximum value inside a subarray and just push it inside an output list. So over here, the k value is basically 3, so the length of the subarray is 3, so you just compute what's the maximum between all these three values. That's 10. Then you compute the values between 5 to 7, which is 7, to 7, 8, which is 8, and 7, 8, 7, which is also 8. And we need to do this in O of n time and O of k space. Unfortunately, we were able to find a problem statement which is pretty similar to this on lead code, and the name of the problem is actually pretty relevant. And before we go over there, we just need to understand that this entire structure is exactly what a sliding window is. Basically, the sub array is your window of length k, and you're just incrementing it and just finding the max value from there. So the name of the problem itself is actually pretty funny. It's sliding window maximum. So that gives you a bit of hint. You can go through the example. I won't go through it, but they've given a pretty elaborate example and the explanation is pretty detailed. So you can go through that, pause the video, go through the link in the description below and try to understand this problem a little better if you've not understood it yet. But we'll just get down to the implementation of it, right? Okay, cool. So the way we're going to implement this, whenever you have a stream of elements which is sort of coming in, and you need to compute the top k values, you're usually using somewhat of a heap data structure or a priority queue. Um, we won't be using any libraries as such, because I'm not really too sure on lead code libraries. But we'll be using sort of like a DQ. While we're doing that DQ implementation, we are also going to be using flavors of a priority queue. If you don't know what a priority queue is, it's basically it's just basically a few rules which helps us maintain what's the maximum value and minimum value which you encountered so far. And a DQ is basically a double-ended queue in which you can either remove values from the back or the front or add values to the back or the front. In Python, it's actually pretty easy to maintain a DQ structure, and the way we can do that is actually by maintaining a list, and you can pop out values based on the indexes as well. So we'll be using that, but before we sort of start, we're going to write a few base conditions as we do always. So if not nums, or if k is less than 1, or if k is greater than the length of nums, in which case we should ideally be returning an empty string, or sorry, an empty array. Now, one other leverage which we don't have is the fact that we can't just print out values. We need to store them somewhere. So we'll be storing our, whatever our resultant set is inside output. And basically we'll be maintaining a DQ structure. I'll just call it DQ, right? Um, One thing which we need to do before we sort of jump into the problem is that we need to identify a few rules, right? Basically break down the problem as much as we can. And the reason why we're doing that is just because we need a better understanding of how we're going to use our DQ implementation. And the way we will be actually doing that is actually by saying that the first thing is that length of a DQ should actually never exceed k, no matter what. Right, so it should always need to be less than k, less than equal to k. Um, One of the other ways that you can sort of look at it is basically that the window size should never be greater than k, which is pretty obvious, right? Another thing is that the values which we're going to be storing inside our DQ are basically going to be indexes, sorry. So values stored are indexes, and the reason for that is basically it will give us a way to reference and understand where exactly does the maximum value which we have encountered so far lie under. And through that, it will help us formulate a lot more things, right? That's the second rule. And the last rule is actually that this is somewhat like a priority queue implementation, but not exactly. There are a few things which might be missing. Um, but if you don't understand what it is, don't need to. You can sort of think of it like the maximum value which is going to be contained would be contained under the first value inside your DQ structure. So max is contained in DQ of 0. So I wrote DP, force of habit, sorry. So yeah, and then basically we'll move on from there, right? Let's just do a quick return output because that's what we're going to be returning. So let's just get down to it, right? So what we'll be doing is we'll be using enumerate. If you don't know what enumerate is, you can Google it. It's basically going to return a list of tuples where you have index and nums as the first and second values respectively. Um, right. So the first thing obviously is that we need to, update the index, right? But we can't just blindly update the index. We need to follow the rules which are there, right? And we'll be following the first rule, which is basically that we need to identify that we're not referencing to some obsolete value. For example, look at this scenario over here, the one which I've highlighted. Over here, window position is all fine. You have from 1 to 3 indexes, where the topmost value is 3, which is our index 1, right? It makes sense. But when you sort of shift this particular window, you cannot reference 3 anymore. And since we cannot reference 3 anymore, we need to update that value as well, right? Or basically pop that index because it's no longer relevant for us, right? So we'll do that. So we'll say if dq exists and dq of 0 is less than I minus k plus 1. If that's the case, then we can say that, hey, we don't need this value and just pop the left value or the first value out because it's no longer required for us, right? Pretty simplistic here. So this is sort of handle that situation for us. The other thing, so we've handled rule 1 and we've handled rule 2. Now all we need to do is handle the rule 3, which is the more important rule, where we need to understand what are the values which are contained inside the DQ. And basically the way we'll be doing this is by doing a while loop inside of for. Again, we are still at an O of n complexity because this will be running at the worst case complexity of O of k, which is a constant. So all in all, you're sort of running off on n, right, altogether. So we're not violating anything over there. So the way we'll be implementing this is by saying while dq exists, right? And the other part is that, as you remember, we are referencing the values which we are referencing are the indexes themselves. So what we'll say is the last value that is there, which was, or the recent value which has been appended, if it's less than the number that we're presently on or iterating on, right? Um, that actually poses a problem for us. The problem it poses is that's not relevant for us anymore. So we can just pop out those values, right? And if we do that, it'll just pop out all elements which are not required. So it just does pop up of all things which are irrelevant. And then eventually when that loop sort of stops running, we append the num value, the index of num. Yep. Um, and we have that. And now all we need to do is we need just one more condition where we need to understand whether I is less than equal to k minus 1, uh, in which case we can actually append the values inside our output array. Reason why we sort of written this is basically because I is going to start from 0, 1, and so on and so forth, but we have to consider the entire window size, right? And before that we cannot make any changes, so till this guy does not reach. So in our case, if our value of k is equal to 3, we don't really need to run anything till I is equal to 2, right? And the value which will be appending inside our output is basically going to be the first value of our DQ, the index of that from our nums. And basically that would be it. Let's just try running this code. Hopefully it should run for us. It does. I've run this a few times and we'll just do a quick print so that everybody understands that everybody's on the same page. So let's just do DQ norms, not norms. Let's just do index. I'm actually not. Yeah, cool. So let's just run this code, get a set of prints, and as you can see here, the output um, is basically this is fine. The output is not getting appended yet, and let's just have a look. Are we missing out on something? Actually, we are. Oh, I sort of switched it. I actually needs to be greater than equal to. My apologies. Right, so nothing is getting appended inside our output till we've reached the second value, which is correct. And at that time, 3 is the computed value. DQ, do remember that DQ is just referencing the values based on the fact that the top value which we have is the greatest element that we've encountered so far. So 1 over here is actually 3, as you can see here. And when that thing gets popped out on the next iteration, um, sorry, over here, when that thing is going to get popped out, it's just going to help us more, right? So you considered 1, 3 minus 1, which is correct. Then you've considered 3 minus 1 and minus 3, which is also fine. But when we come to minus 1, minus 3, and minus 5, which is basically uh, an iteration after our 3, we need to pop out the values which are irrelevant for us, and we have done that, and that's just the entire implementation, right? So pretty simplistic, we've used flavors of a priority queue, and we've implemented this entire thing. If we had any libraries which we could use, we would just use heapify library, which is in Python. But yeah, so I've submitted this thing, and you can see it's 75% faster than the other solution, which is pretty awesome. Again, you don't really need to look at this, but it's a good thing to note on how you can optimize your solution. Again, we are running this on OFN, so we're not breaking any rules, and the maximum size of a DQ is also going to be O of K, so no rules violated there either. All right, cool. So that's it for this problem. As I mentioned before, you don't really need to get intimidated by all these problems, and there are going to be billion ways of solving this problem, and you can solve it howsoever you like. This is just an approach which I find a little bit easier for most starters, right? There's not much here, as you can see. It's just doing a few pops here and there and just doing a few appends, and the crux of the problem, once you understand how to use the DQ structure, you can just use the entire implementation, right? All right, cool. So that's it for this video. If you have any doubts, do give it in the comments below. And if you like this video, do give a like and do subscribe if you can. We're pushing videos on the daily, and it'll be awesome if you could join us. Um, Again, if you've already subscribed, you're awesome. We all know it. And have a great day. Thank you.